All right, everyone. Well, let's see how this works, right? Now, I know that we've already run into our first problem, which is this cat. All right, Zoe. Zoe, this is me. I gotta work, okay? You gave me cat scratch fever, so you're gonna have to leave me alone. All right, everyone. So this will be interesting. This is the best I could come up with. I got the camera rigged up. Maybe I ought to put out some cat food and we'll see if we can get these things out of the way. All right. I promise they're not green screened in. Let's go back to classwork and let's do some review of Friday's lectures, which maybe some of you are actually looking at just now, since it took me a while to figure out how to get that onto YouTube. It's just some weird computer problems I have at home. Okay, now hopefully we're all okay with kets. Kets are easy. They're basically wave functions, not quite, and again we will be covering that soon. But there's this dual correspondence thing, and it takes a while to understand bras, and we're just going to largely learn by doing. A good way to think about these right now is let's look at alpha beta. Remember, this is an inner product. Let me write that down. An inner product, and it's equal to a complex number. So when you see these are numbers. Don't forget that. And one of the things that we covered last time was that if you switch them around, which you do a lot of when you're doing proofs, that it becomes this complex conjugate, and often it's a complex number, and that means it can have a real and imaginary component. Now here's a hint. In the future, we're going to see that this is actually the integral of one of the wave functions times the other. Okay, so that's why, and this is called an overlap integral. So I'm jumping ahead a little bit, but this is what the symbols mean in Dirac notation into the world we just recently stepped out of, where there's integrals everywhere. There's also outer products. Looking at the camera. Outer products. So just take the inner product and reverse it. And so it's like alpha, beta. And this is actually an operator. So one of the things we're going to learn how to do is turn some of the operators into Dirac representatives. And it's actually going to take us a while to bridge that gap, but regardless, while the inner product is a number, and hint, you probably are some idea of what two wave functions integrated, that's not hard to visualize, right? Well, and that's what this is. So these really are not hard to understand. An outer product is an operator, and we're going to understand that quite a bit better today as we do more stuff, more examples. As I mentioned, anything with a bra in it can be confusing, and we'll learn by examples. Okay, now let's see. Now we also had for operators, and I've got to be careful. There's a panther right here, it's slightly outside the camera, but she may come into the frame here. Okay, for an operator acting on a ket, the dual correspondence is this, where you have the adjoint of the operator, and I know that's kind of confusing. Now for Hermitian, it's like, well, how are these operators different? For Hermitian operators, which is almost all of them, almost all the operators that we have covered or will cover, they're exactly the same. Not always. In fact, I'll show you even a function of operators and how those are a little funky. And it'll be about a month before we start covering more non-Hermitian operators. So my point being that for the most part, how an operator changes when you're talking about bras or kets, for the most part, the operators don't really change. And when they do change, it's not trivial to figure out how the two are related, but there's always a clever trick, and we'll get it, so there's nothing to worry about. Okay, something else that's important, really, really, really important, is this little rule. And I'm not invoking hermeticity here. I'm just writing this down in general. This is still true of a Hermitian operator. What I'm doing is, let's see here. Now, before I do anything, let me first associate. Let's associate the operator is acting on the ket. Now, you know I could do it on the bra, but I'm going to do it on the ket. All right. Now, I want to flip things around. Now, if I'm going to do that, I'll first do the I'll do the ket to a bra thing. So there we go. Again, doing what I just did before. All right. Now, next step. Next step is that if I made the ket, the alpha ket a bra, I really have to do the same thing with the beta bra. It has to become a ket. Now, the reason is it's just one of the Dirac rules. You can't have two bras at the same time. That just is nonsense. You're just talking nonsense. So I'm just flipping everything around. The important points are to remember that the operator is now adjoint. Not that generally matters. The operator acting on a ket is still another ket. So when I flipped, beta alpha, alpha beta, you got to remember that you also pick up a complex conjugate. Oh my God, look at that. What is wrong with me? It's like I have COVID or something. Anyway, right, little star means complex conjugate. And you know I cannot draw stars. It is almost impossible. Anyway, all right, so for Hermitian, and I'm still largely reviewing, for Hermitian operators, let's see, where the thing is equal to its adjoint, and that includes momentum, the Hamiltonian, just really everything we've covered. Let's have that operate on a ket, and it will be an eigenfunction of that ket. So this A prime state is an eigenfunction of this operator, whatever that is. And A is not complex. Now, I don't mean that it's, has a basic personality. It has no letter I in it. That's what that means. And there's not much else to say. It's just convenient. Okay, so that's number one. Here's number two, which is that usually operators, when they have some eigenfunctions, they have a bunch of eigenfunctions, usually an infinite number. Actually an example that is not like that are these spin up and spin down. There's only two. When it comes to like particle in the box, well, there's an infinite number of those. All right, what we covered last time is that the inner product of two states, remember that a bra, we want to think of this as like, this is the projection of this ket into this state of the, let's say that's the ground state and that's an excited state. Let's say we're talking about particle in a box. Then the overlap is a Kronecker delta, which is that if you're not talking about the same state, it's zero. If what I'm saying here in this math speak is that if you're not in the same state, if it's one, if A prime and A double prime are the same state, then you're just saying that the wave function is normalized. So that's orthonormality. So that's true of all the states of a Hermitian operator. And I said this last time, I wanted to give a little bit better example than I did last time, and I'm having to try to line up the paper here. Recall, let's draw the ground state of, 0 to L. So let's draw the ground state of a particle in a box, and the first excited state looks like this. And so if this is the first excited state and this is the ground state, then that's zero. And as I mentioned, the overlap of the wave functions is the integration of the two multiplied. And what we have is an even times an odd function. And hopefully you remember your calc enough to know that that's zero. Okay, now what do I want to say now? I gotta make sure I don't get lost in my own notes. All right, so this has just been a review. So now let's come over some new stuff. All right, now what can I do here? Let's learn how to write things in terms of a basis function. So something you've heard me say a zillion times, I'm going to say it again. You can span Hilbert space, excuse me, COVID kicking in there. You can span Hilbert space with a complete set of eigenstates. All right. So I'm going to draw an arbitrary state here. And again, I love my particle in a box states. Here comes a visitor. Well, let's hope that she passes without doing. Yeah, she passed on. Okay. So I love my particle in a box states. So I can draw any wave function inside of this box as a summation of enough of these, and I have an infinite number to work with. And so now I'm going to write this out. I'm going to write it out a little differently than the book writes it out, a little bit better notation. So I'm going to sum all the states. I'm going to make a sum of all these particle in a box states. I'm going to have some weighing coefficient to give, define the amount that they input into some other state, this alpha ket, which again is something that I could draw. Let's just say that alpha, well here, I'm going to go ahead and do a little preview and tell you what a wave function really is. I've told you this before. It's really a x bra with an alpha ket. So my cat who just came by drew this, for whatever reason the cat drew that. And this squiggly line can be represented as a sum of these particle in a box states with some appropriate weighing constant. So again, I just want you to, this sometimes can, it's a bunch of symbology. I know there's a bunch of symbology, but this is what it means. So you can visualize this, right? All right. So, what do I want to say here? So let us. I'm writing this out with this little n thing because I wrote this out wrong. A to the n. I wrote this out wrong. C a to the n times the a to the n state. So the way you want to write this out to connect it back to the book, the book is obsessed with these kets that they call A prime and A double prime, and that can be very, very, very confusing sometimes, and it's not helping that my handwriting is not so great right now. So anyway, I'm just trying to connect back to that. I'm using this little n notation because I think it'll be a little bit less confusing. But what I'm writing out here is the way the book likes to write it. I just find that it can get really confusing once you've got prime. It just can get messy. So I'm doing it this way instead. Okay, sorry for a little flub there. Okay, now let's project. Onto the A prime state. So we have a bra, an A prime bra, on the left. Okay, on the left of this ket on the right. Okay, so what I'm doing here is I'm writing this, and what is that? That is going to be A prime. Okay, so now again, as you are just learning the rules of Dirac notation, what you do, this is on the left, I already told you that I'm going to write this summation. There it is. Okay. All right, now this can go inside, all right, and again, if you're wondering oh, well, how would I know that? It's because it's a game, and it has rules, and you're seeing the rules for the first time. So if you're looking at this thinking, oh, well, maybe I should have known that already or something like that, no, but you know it now because I'm showing it to you for the first time. Okay, now here we see that we've got ourselves an inner product, and we've already talked about that this thing is a Kronecker delta of A prime and A to the n. Okay, now this is just a pure logic. Okay, it's just equal to a constant, right? Okay, now let's think about why this is. Kronecker delta says that unless you're talking about the first term in this sum, which a to the n is A prime, inner product is 1. Okay, so that survives. But when I've got n equals 2 and to infinity, this Kronecker delta makes that component of the summation 0. So the only thing that survives is a prime, which due to orthonormality, the normality part, that's 1, and you're only left with the coefficient of, the first coefficient of the first A state, right, which I call A prime. All right, so what this is saying that this arbitrary state alpha, which is composed of a whole, let me be very exact, is composed of a whole bunch of particle in a box wave functions. All right, so yeah, let's use the particle in the box here. So this thing that my cat drew is composed of a function of all these with some weighing coefficient. All right, now what I'm asking here is how does that state map onto the ground state? Let's call A prime the ground state, just make it easy, right? Well, it's just how much weight that first state contributes to the overall wave function via the proof that I did right here, most importantly this Kronecker delta function. So the Kronecker delta function turns this summation of n into this a to the n, the summation of all possible n's to simply n a prime, the first one. It also got rid of that summation, right? Because all the terms were 0 except 1, so you don't have a sum left. All right, now what can I talk about? Let's see here. What else can I do here? Oh, okay, now this is very important. This is very important. Now I'm primed to show you the most important thing I can ever show you. Now, as I promised, Dirac notation simplifies all of quantum mechanics real well. And what does that mean? When I've been telling you for so long that Dirac notation simplifies quantum, it's because of what I'm about to show you. I'm screwed up there. See a to the n. You see how I saved myself? I wrote a to the n and I meant c a to the n. Anyway, there you go. Okay, so there we go. I'm just saying by definition. All right, now what I can do, I just defined what the coefficient is. So I can do this. A to the n. A to the n alpha. Okay. And I know that because this right here, right, so this ket here is right here. This here is the same as this here. Just want to make sure you see that. All right, you see those are the same thing. That's there. Okay, and your coefficient is this overlap, right? Just like I used it somewhere previously. Where did I use it? No. Actually, I'm already confused. But anyway, yeah, the overlap of the state onto any particular of the eigenstates is the coefficient. Let's see. Now, what do I want to say about that? Now, what's terribly important about this is that. Sorry, I'm just checking my notes. I want to make sure I didn't say anything stupid. What I want to point out about this is that if this is alpha, okay, so alpha, right? So just alpha. Okay, if that's true, then this is equal to 1. Okay, so therefore, sum of states of this outer product, right? That's an outer product, is equal to 1. Okay, this is gigantic. Check. This is the best friend you'll ever have in this quantum mechanics class. This is called a completeness. A completeness relation. Or a closure. Okay, again, those are the words. You'll see those words in papers and whatnot. What's more important is the application. Okay, an application is called, and don't forget this, resolution of the identity. I'm going to pray that that's spelled correctly. I have no idea. Okay, That is gigantic. This is so helpful. This is how you make your way through proofs. This is how you can take an expression that's unbelievably gigantic and make it small. Sometimes you want to make small expressions and make them real big. And you only make headway on proofs because of resolutions of the identity. I just cannot emphasize how much trouble this thing saves. And so let's go ahead and start using it. Let's use it for a gazillion things. Okay. Let's see. How about we do a proof? Okay. So proof. And I'm just doing something just off the wall, random. Okay. So I was talking about this earlier. N equals 1 to infinity. I'm just writing this alpha thing out again. A to the n. So some weighing coefficient. Right, so that's an inner product. It's the inner product of the state with whatever nth eigenstate of the operator. A to the n. Okay. All now here's what I'm trying to prove. All C a to the n's are between 0 and 1. Okay. So what I'm saying is now. So remember that this thing is equal to a to the n alpha. That's what that is. It's an inner product. It's complex. But regardless, the absolute value of this complex number is between 0 and 1. I contend that the weighing coefficients are between 0 and 1. Okay, why? Right, let's go from there. Okay, here's the proof. Now, as in a lot of things, I happen to know what the right starting point is. And of course, I'll always make sure you have the right starting point. Okay, now I promised you that we're going to be resolving identities, right? All right, so let's do that. Okay, now here's how you resolve an identity. Okay, I've got to give myself a little bit of room. Okay, here's alpha. Now I'm going to resolve an identity, and I do that by putting a sum out here. And now I've got to put in a to the n. Right, here's the outer product. And I've got my sum, so this is 1. Okay, there we go. Okay, so this equals sum, n equals 1 to infinity. Now I'm going to flip this guy, just for the hell of it. Just, I feel like it. Now I got a complex conjugate. Oh, I drew the star right. Did you see that? I drew the star right. That's so rare. Okay, and now you should recognize this as C a to the n star, C a to the n, which is the sum, infinity, C a to the n. There we go. All right. Okay, well, so what? Well, alpha, the inner product due to orthonormality is equal to 1. So all this has got to be equal to 1. So therefore, if the sum of is equal to 1, then all the coefficients themselves have to be between 0 and 1. They have to be. You can't have a square, an absolute value of a square. It can't be less than 0, right? That's impossible. That's absolute value. And none of them can be greater than 1 because then they would sum to greater than 1, right? So no single member of the summation can by itself be equal to 1 or greater because then the sum would automatically be equal, it would be greater than 1, but it can't. So there you go. So anyway, that's a simple little proof. It's not really that important, but the important thing here is to see how you take this and you kind of put it right in between to see how you resolve identities. That's terribly, terribly, terribly important. Okay, now let's do another one. All right, let's start figuring out how to understand operators better. Okay, so let's say for operator, and I will use the letter A. Now your book loves the letter A, and I tend to use omega because that's more what when I use omega, you tend to see that more in the literature. This book loves the letter A and B, but I'll use A because for this operator acting on A prime, so A prime and A double prime and A triple prime are all eigenstates of the A operator. So that's what I mean to say. Okay, so what? All right, let's see. What do I want to prove? I want to prove that the operator A is equal to this. So I'm going to sum all my states. Here's the eigenvalue, so that's a complex number. If A is Hermitian, it is a real, it is purely real. And there's an outer product. Okay, so how do I prove that? How do I prove that? All right, here's what I'll do. I'm going to resolve. Okay, how do you like my shorthand? Resolve two IDs. All right, how do I resolve two IDs? What does that mean? Okay, what I'm going to do is A is equal to, I'm going to go ahead and write, and prime equals 1, so I'm going to have to be careful. I'm going to have two resolutions. That means I have two summations. Now I got to be careful, so I'm going to call the first one an n prime from ground state to all excited states. The other one will be just n. Okay, since I wrote n prime first, I'll start with that outer product first. Okay, then here's A, and then now here's the other guy, the not prime. Okay. So now we know that an operator acting on a ket, especially its own eigenstate, I mean, I've already told you what this is. It's a to the n. You know, you just get a numbered out. Okay, now what that means is, okay, let me draw this below, that this is a to the n, again, the same eigenvalue, Kronecker delta n prime n. Okay, now what this means is, all right, so what happens is, when you operate on this state with this operator, out comes a number. So let's pop it out front. Okay, then what you're going to have is an inner product of a n prime with a to the n, which is a Kronecker delta. So maybe I should have gone a little slower, right? But anyway, so this, sorry. Yeah, I should have done that. This turns into this, which is actually equal to this. So sorry, I didn't really do this in the best order. I hope you can follow along. It's not hard at all, right? Let's see. Okay. Tell you what, make it clear. I'll just write that out again. Okay, I'll make it more clear. Okay. So the first thing to note is that I'm going to get rid of one of the summations. The Kronecker delta is going to do that. Here's our eigenvalue from this, right? Now this guy is still here, but it's not n prime anymore because the Kronecker delta makes all the n primes equal to n. So this is this part, right? So again, when this operator operated on this ket, it kicked out an eigenvalue, and that's here. Now, what's then left is the overlap of an prime with an, which is a Kronecker delta, and that is 0 unless n prime is equal to n. So you notice that what I've done is I've taken all the n primes and I've just written n, and these guys are the same. Now that was completely arbitrary. I could have said, instead of saying that all these guys here, all these n primes, are now equal to n, because otherwise everything is 0. I could have equally just said these n's are n primes because otherwise everything is 0. I just simply made a choice to go with calling the n primes n. It was arbitrary. Okay, now this guy, hopefully you recognize that as 1.0. You know, you've gotten sophisticated enough with Dirac notation to recognize that, and I told you how much Dirac notation makes things easy, right? You'd have to do some crazy integrals to prove that. And you don't have to do any integrals at all. with Dirac notation. Okay, so what are we left with? Is equal to n equals 1 to infinity, a to the n, a to the n. This is 1, a to the n, which is what I set out to prove, right, from the very beginning. Did I do it right? Yeah, I did it right. Okay. So there you go. That's an example of a proof with Dirac notation. And let's see. Let's do a couple more things. Let's see. What do I want to do next? Okay. So your book goes off a little bit on something called a projection operator. So let's spend a little bit of time on that. I don't know that this is really that important. Oh, looks like I'm out of power. I'm going to take a little bit of a break and power the thing back up. I'll be right back. All right, everyone. Had a slight power problem, but blame COVID. Let's see, where was I at? So I wanted to talk a little bit more about what this thing does, and just this part, this outer product. We're going to call it, let's just say it's a ground state. Just give ourselves not an ambiguous end state. Let's go with a prime state, and again that'll be to use the language of book. So that's like the ground state. Okay, and let's operate on state alpha. Okay, so what do we get? You get a prime ground state overlapping this nebulous alpha state. And by definition, this will be how much this alpha, I keep wanting to call it gamma, how much alpha is in the ground state. There we go. Okay. Now, in terms of like your sophistication with quantum, let me give you the right description of what just happened. What you say is that this operator selects the component of the alpha state that's parallel to the A prime state. Or let me say that again. This operator selects the component of this alpha state that is parallel, and let's say alpha is the ground state, so it's parallel to the ground state. And again, this is just a weighing factor. It tells you, by the way, I think we'll get into this a little bit more later, but this number, this inner product, the absolute value squared, is actually the percent, like the percent character that alpha has into the ground state. So anyway, yeah, I don't want to say too much more about that because I think we're going to cover more of that later. Okay, so that means that this guy, it gets a special name. It's called a projection operator. So this will come up in some more proofs. I want to say a little bit more about it. One of the ways to write a resolution of the identity is to say this is to take the sum of projection operators. All right, so that is a resolution of the identity, so that's equal to 1. Now I just blabbered on at length about how to write an operator in terms of a sum of eigenvalues, and it looks like projection operators. I keep wanting to put a little a, but it's not an a. I have to work really hard on that. And another property that I do see come up every now and then is this. So I am going to square this thing. Okay, well, why am I doing that? Well, it has a property that is used in various proofs. Would make a real easy homework question too. Okay, so you may notice, what's that? That's 1. So it's equal to itself. Okay, the point of this is that this operator is equal to its own square. All right, so they're equal. And therefore you call it idempotent. Idempotent is what that means. And again, that's used in proofs. Okay, again, part of Dirac notation is learning how to do proofs just for the hell of it, and they're much easier to do with Dirac notation. So let's do another proof. Let's see what else we can do with projection operators. Okay, let's say, all right, so if I will do the projection operator onto state alpha, and again, you know, I've just noticed now I've written the same thing like about 100 times. Okay, then what am I going to do? What I'm going to do is I'm going to take this projection operator and I'm going to subtract 1 from it. Now let's look at alpha. Okay, so what does that do? So this would be a good take-home question, right? You should be able to handle this. The trick is, all right, so first, all right, let's say take-home exam and you get this question, like, so how do you even begin? Well, the first thing I would do is note that just put down the operator, put down the projection operator. Okay, so there you go. Now, if there is a trick, if there's anything in here that you're like, well, I don't know what the next step to do is, I wrote a 1, and from now on, you need to be inserting resolutions of the identity. All right, so now you may see that where I'm going with this. So now write that outer product, and yeah, there we go. And now it's going to operate on the alpha state. Okay, so what? Well, now I can just look here and I can see that when this guy is here, let me just write it, A prime, okay, minus the sum of all states A to the n on alpha. Okay, now check this out. When n is equal to 1, these are the same thing, right? When n equals 1, A prime alpha. A prime alpha. Okay, so when n equals 1, this is 0. So what's left behind is the sum of all states. And again, let's call n equals 1 the ground state, just to use familiar language, just so you're comfortable with this. And that's fair. A to the n. A to the n. Okay, so therefore, the projection operator minus 1 is minus the sum of all states. It's kind of obvious now. Okay, so the projection operator minus 1 is the negative sum of all states except the A prime state. Okay, so therefore, if you project that, oh, look at that. See, I wrote an A. I told you I'd write an A. Okay, so now I've written the projection operator, and now I'm going to project that onto this, which is automatically 0, right? Because I am projecting this, which has no A prime component, only higher states. I'm projecting higher states onto the A prime state, the ground state. Well, that's nothing, right? That's nothing, because what you're ending up with is what I would have ended up writing a whole bunch of times is A prime, A double prime. Let's see. Anyway, all those are 0, right? So I hope you can follow along. I don't really feel like that I need to go into such explicit detail from here to here. I'm hoping at this point it'd be quite obvious that given that this does not contain the ground state, when I project onto the ground state, well, there's nothing there, right? So 0. Okay, last bit in this somewhat torturous class session. Hopefully only 2 more of these is over. And how am I doing on time? Let me check the time, because I don't really care what time it is, because I'm just kind of gonna do this as a lesson. I think I'm gonna try to. Hopefully I'm about an hour, but I have no idea. It's COVID's fault. It's not my fault. What am I doing? What I want to do is talk about functions. Functions of operators. Okay, so this ends up looking hideous, but it's really easy. This is like one of the easiest things that you'll see. It looks cool, and it looks cool, but then it looks cool because it's hard, but then you find out it's not hard. Via Taylor series. Okay, let me remind you what a Taylor series is. For a function of x about a. So what I'm doing is I'm trying to describe a function f of x centered at point A. F of x near point A. This is the terminology I usually see describe this. Okay, so you start with whatever the value is at point A, but the point of this is then you're going to be moving a little left and right of point A. Okay, so there's the linear term, then you get a nonlinear x squared term. Okay, x minus a squared, and on and on and on. Again, from what, middle school? When did you learn that, middle school? Okay, now here's what you do. Assume x is your operator. I'm going back to my generic little gamma there. And of course you're centered about 0. This is like a displacement. It's a displacement. Well, we're not going to displace the operator from itself, so we just call it 0. All right, so therefore, f of a function of an operator, my favorite gamma, is f of 0. Again, 0 is the displacement, plus f prime of 0, gamma, 1 factorial is 1, plus f double prime of 0 squared over 2 dot dot dot. Okay. So again, I just made a0 and x gamma the operator. Okay. So let's do an example. So it's like, all right, where am I going with this, right? Before I do that, I want to make sure that this is clear, because I bet this is kind of confusing. I mean, I know it's just a Taylor series and I've given some explicit rules, but I bet you it's still a little confusing. So, because it's operators. Operators are different. I just rattled on and on about how they're different. Okay, so let's do this one. Okay, here's our operator. Let's square it. Right? So let's apply that to this. Okay, so our operator, our operator is clearly this. Our function is basically x squared, right? Now, there is no x in this question, but anyway, it's just going to make this easier. Okay, so now let's expand this as a Taylor series. Almost forgot the square, didn't I? Okay, now the function x squared as 0 is 0 squared, which is 0. Right? 0 squared. All right, that doesn't do much. Okay. Next step. Okay, the derivative of x squared is 2x. 2x at x equals 0 is 2 times 0. Okay, well, that's automatically gotten us nowhere. Times the operator. Okay, well, we're still nowhere. But wait a minute, we really shouldn't have a linear term, right? So that's good. Okay, next term. Okay, the double derivative of x squared is, okay, the first derivative is 2x, the next derivative is 2. Okay, 2, there's no place for a 0, it's just 2. Okay, 2 over 2, that 2 is right here. Gamma squared. That's all there is to do. Okay, now the triple derivative of x squared is 0. So what I've I've proven that the operator squared is the operator squared, right? That's a little stupid, I know, but it hopefully calibrates you on how to do this. All right, and it's not hard. That's part of my point, it's not hard. All right, last bit, we're almost done. We're almost done for today. Okay, let's do this one. This is by far more interesting, right? Hey, what if this operator is a momentum, right? What's e to the derivative? Yeah, I bet you never thought you'd work on something like that. Well, this ends up being real easy. 1 plus operator plus operator squared over 2 dot dot dot. Right. So real easy. Okay, now let's say that using book terminology that it's the A operator and that the A operator operating on its own basis set, of course, does exactly what it's defined to do. Of course, it's going to do what it's defined to do. What do I want to say about that? In which case, f of A acting on A prime is actually equal to that function of the eigenvalue, A prime. Okay, now it may look like wait a minute, what did I just do? What I've said is, all right, I have a function of an operator. The operator is A prime. The function, let's make that e to the operator, right? So that's the function. So, i.e., e to the operator A. Okay. And based on this expansion, that's 1 plus the operator. Hell, I've already written all this down. I don't know why I'm doing that. Well, I'm committed now. Okay. But now let's have it operate on A. A prime. In which, oh God, sorry for my handwriting there. I really kind of screwed up, didn't I? But I'm committed now. Okay, so what is this equal to? It's equal to 1 plus A prime plus A prime squared over 2 dot dot dot, which guess what is equal to e to the A prime. Okay, so therefore e to the A acting on A is equal to e to the A prime A. Okay, 1 second. I gotta get that. It's probably the hospital. All right. Sorry, folks. I'm dealing with everyone keeps calling me asking if I'm still alive or if my leg fell off or something like that. Anyway. Okay. So there you go. Right. So now the point of this is that I know this looks like, oh my God, what do I do with that? It ends up being insanely easy. Right. So that's the point. This is actually really easy stuff. And guess what? We're going to be dealing E with to an operator a lot. Okay, now let me give you another example. Let's say an operator is the form of a matrix. Right? Because I told you you're going to be doing a lot of that. All right, so what is E to the A? Therefore, what is that? What is that equal to? It's really easy. E to the A, E to the B, E to the C, E to the D. There you go. All right, just another example of how this is actually really quite surprisingly easy to deal with. Okay, last bit, transposes. Sorry, let me line up. Notebook, transposes. Let us deal with a bra A prime on F of A. And I need to transpose it because I'm in dual space, right? Okay, let's see here. Now this is going to be equal to F star A prime. Okay. Now that is just, this is just a statement. This is just another one of those how it works in terms of functions of operators acting on bras. You just saw what happens on kets. This is what happens on bras. And if you're looking at this and thinking, well, how do I know that? You shouldn't. I'm telling you, right? So remember that a lot of the lessons that you're getting now are, this is the rules of Dirac notation. I don't know that you can generate that knowledge on your own. So you shouldn't be frustrated or anything. But here's the cool thing. We actually have covered enough to prove it. Okay, now, A prime, I'm going to prove it. F of A transpose, and I'll write a different state on the right. Okay. Now note that what I've done is I've clearly associated these two, right? Remember when I'm operating on a bra, I need to have the transpose. So clearly I'm thinking about these two are working together. All right, now I'm going to use that formula that I said was so important before. What I'm going to do is I'm going to take the A prime state, that bra, and I'm turning it into a ket. Okay, so no more transpose, but of course now I also have to turn that ket, if I turn the bra to a ket, I have to turn the ket to a bra, or you're talking nonsense, so don't forget that. And I've literally flipped everything around, so I get a little complex conjugate, and you should give me congratulations for writing the star correctly. All right, let's see. Now these, we just talked about how to deal with this. So this is f of the eigenvalue, so e to the eigenvalue if the function is an exponential, and that just leaves behind this arbitrary wave function psi, which I don't know what it is, it doesn't matter. Okay, star, and that's equal to the complex conjugate. Okay, so notice that this part here is what I was trying to prove. So there you go, that's the proof. So like on a lot of your homework 2, number 4, when you're trying to figure out how to manipulate operators, you work on a dummy. You have a dummy state, in this case a dummy ket or maybe a dummy bra, and you have to then follow some rules around, and you figure out how to generate these proofs. Okay, now I want to just apply this to a very important example. I want to start introducing you to something that you're going to see a lot of, which is the time evolution operator. Let's say for an operator H, which you know is the Hamiltonian, and it has its own eigenstates, which I call the true wave functions. And of course it spits out the energy times the state is still there, right? This is our eigenvalue equation. Okay, so what do I want to say about this? I'm going to write a function of the Hamiltonian. It's going to be a mouthful. Look at that. Look at all that. That looks horrible. Okay, but at this point, you should know enough to know that I'm just going to write down the eigenvalue. Right, so there's not much to it. So again, right, this really is not that hard. I've just taken the operator and I just inserted the eigenvalue. So hopefully you've seen that enough times that it's not like a mystery. Okay. Now, this is kind of important, and that is that what I want to do is I want to deal with the transpose of this. Now, the Hamiltonian corresponding to something real, energy is real, means that the Hamiltonian is Hermitian. But this operator of the Hamiltonian, this function of the operator of the Hamiltonian, it's important to say it right? This function of the operator, you can't really say that it's Hermitian. You have kind of different language for this stuff, which is something that's coming up. I don't think you can say it's Hermitian itself. Anyway, let us look at what happens when we're in the dual space. T over H bar, okay. Okay, right, so there's the bra, here's the operator, I've written the transpose, and from what we've seen here, what I've got to do is write the function with the eigenvalue. So I change the H bar and it gets E prime, which is, like 1 EV, whatever the energy is of the state, of the E prime state. So let's say that it's 1 EV. Okay, so there you go. Now again, what I've done is I've said that the result, the e to the eigenvalue, I've got to write down the complex conjugate when I'm in dual space. Now what this does is it gives me a way to figure out what this actually is. And what it is e to the I, it's basically the complex conjugate. Let me write that out completely so that you take it all in. I don't like doing it like this. Anyway, okay. So this function of a Hermitian operator, the transpose, the dual space of adjoint. Sorry, God, ugh, so many words. The adjoint of this function of a Hermitian operator is actually the complex conjugate. And this is going to be really important. For one, what you've seen a way to figure out what these adjoint operators are in this case. And remember, for Hermitian operators, the adjoint is the same as the operator. I've done a function of a Hermitian operator, and you see that we've got a little bit of a difference. And you saw how I figured it out. So when you have adjoints of operators that are not Hermitian, or functions of even Hermitian operators, you have to do a little bit of work to figure out how these are related. And you've just seen an example of that. You've also seen, this is, by the way, the time evolution operator. Once we're done figuring out the rules of Dirac notation, we're doing that next. So I want you to see that now. All right, now, there is a cat driving me crazy, and she is playing with the string I've used to tie up the projector. So maybe I can, you want to say hello? You want to say hello, Charlie? No, she doesn't want to say hello. But anyway, thanks you for putting up with this. Come here. Come here. Come here, Charlie. Tell you what, let's see. There's Zoe. There's Zoe. She likes to sleep on my stuff. And Charlie's about too. And anyway, so I've talked too long. I will see. Oh, there's Charlie. Say hello, Charlie. There's Charlie. All right. I'll see you all on Wednesday. Bye.